I will be presenting our work on evaluating task performance with non-collocated force feedback driven by signal-independent noise. Hi, my name is Chua, and my co-authors are Alison Okamura and Daryl Dio. In this video, I will go through our motivation for looking at signal-independent noise in non-collocated haptic feedback. I'll then describe the experiment we conducted to evaluate task performance with non-collocated haptic feedback under different magnitudes of signal-independent noise. I'll then discuss our results and end by sharing some future directions and conclusions. In able-bodied people, the movement of a limb is accompanied by haptic or touch feedback in that limb that comes in the form of proprioception, kinesthetic force feedback, and tactile feedback. These haptic feedback signals can be used in closed-loop motor control. Even in teleoperated robotic systems, we can render haptic feedback to the target limb that is generating the control signal. Uses of motor and communication prostheses, such as the Intrecortical Brain Computer Interface, electroencephalogram brain-computer interface, and the surface electromyography interface, generate control signals from the attempt or intent to move a limb. However, because of loss or diminished haptic sensation due to amputation or paralysis, they cannot receive conventional haptic feedback. Non-collocated haptic feedback is when we relocate haptic feedback from the active limb generating the attempt or intent to move to a location of the body where sensitivity is still intact. This has the potential to provide haptic feedback for closed-loop control of prosthesis. Of the prostheses I mentioned earlier, the Intrecortical Brain Computer Interfaces, or IBCs, are an emerging form of neural interface that have demonstrated good performance in the control of both communication and motor prosthesis. Little work has been done to explore haptic feedback for IBCs, and it will be the focus application for the presentation. One unique characteristic of IBCI systems that affects haptic feedback is that their output contains signal-independent noise. This is unlike physical movements and sEMG signals, where noise is signal-dependent, and the amount of noise varies with the size of the motor command. In IBCI control, however, noise is signal-independent, and thus it is invariant to the size of the motor command. This signal-independent noise makes its way into the haptic feedback loop and led us to ask the following questions. Can users of systems with non-collocated haptic feedback tolerate some amount of signal-independent noise without diminishing task performance? We predict that there will be a threshold under which they will be able to do so. Secondly, will the amount of signal-independent noise influence how users perform a virtual localization task using non-collocated haptic feedback? We predict that users will attempt to increase the signal-to-noise ratio, such that it will be above the threshold that inhibits their performance. This is possible because the noise magnitude does not increase with a larger input signal. To quantify the magnitude of noise and the signal-to-noise ratio, we use the coefficient of determination, R squared. This has been used by others in the IBCI community to quantify noise magnitude as well. It is a measure of the variance of a noisy signal explained by the clean signal. Thus, when we fix the range of clean input force and look at the output force, which is the clean signal plus the noise, a lower R squared indicates a noisier signal compared to that with a higher R squared. For example, a clean signal with no noise has an R squared of 1. A low noise signal in our experiment has an R squared of 0.85, and a high noise signal in our experiment has an R squared of 0.65. We can also use R squared as a measure of signal-to-noise ratio. For a fixed noise magnitude, a higher input force gives a higher signal-to-noise ratio and a higher R squared. To test our hypothesis, we conducted a user study with the following hardware setup. We used two haptic devices, one for position input and one for non-collocated force output. In the virtual environment, users are presented a surface with an indentation. The task is to find the center of the indentation using the available haptic feedback. They are presented with a top-down view of the environment with surface features occluded and a plane projection of their 3D cursor to eliminate the depth cues. Thus, there are no visual cues as to where the indentation is located. The noise is generated as a displacement and low-pass filtered at 2.5 Hz. We then use Hooke's law to derive the noisy force component from the penetration of the noisy displacement component into the virtual material. The constant C is a predetermined scaling constant that results in the R squared values we used in our experiment. Lastly, we render the output force as the virtual interaction force plus the noisy force. We performed a within subjects user study with 20 participants and 3 magnitude levels of signal independent noise: no noise, low noise, and high noise. We gave users 30 seconds of free exploration of our virtual environment to familiarize themselves with the cursor inputs and non-collocated force outputs. We then gave them 8 mock trials of 20 seconds each, under the conditions of no noise and no visual occlusion, so that they were familiar with the experimental task and protocol. We then evaluated their performance over 3 noise magnitude levels for 5 20-second trials each, in pseudo-randomized blocks of 3. We measured several performance metrics: the distance error of the guess, time per trial, mean peak output force frequency, mean peak output force, mean peak input speed, and mean peak input displacement. For the last 4 metrics, we only considered the last 5 seconds of trials where the guess of the indentation location was within the radius of the indentation itself, as this was the area where there was meaningful haptic interaction and position localization. Our results suggest there is a threshold of noise below which users do not suffer any meaningful performance degradation in our task. This is because both the distance error of the guess and the time per trial had a significant difference for both the no and low noise conditions compared to the high noise condition. Our results also show that users were attempting to increase their signal to noise ratio. We see that the mean input displacement increases as noise level increases, with a significant difference between the no noise and the high noise condition. The signal to noise ratio increases because there is a greater amount of in-plane displacement during localization that would result in greater penetration of the virtual material when localizing the indentation, and thus theoretically higher interaction forces. However, users' attempts to increase the signal to noise ratio this way were not effective, as there was a saturation of the output force on the device. In this work, we did not find a significant difference of the output force frequency between noise conditions. This might be because there was no benefit of varying movement and therefore output force frequency when noise frequency is fixed. However, it might be helpful if the noise frequency was varying, and thus future work can explore how the frequency of the signal-independent noise can influence users' movements. In this work, we measured users' performance in a 3D localization task when presented with non-collocated haptic feedback under 3 magnitudes of signal-independent noise. Our work suggests that there is a threshold of signal-independent noise that users of systems with non-collocated haptic feedback can tolerate without degradation in task performance. However, we would like to point out that this threshold might be task-specific. In general, designers of devices with non-collocated feedback with signal-independent noise could possibly tune the amount of signal smoothing to achieve a balance between system bandwidth and usability. In the face of increasing magnitudes of noise, users will adapt their movements to increase signal-to-noise ratio. However, this is of limited usefulness if the device saturates. Thus, designers of future systems could ensure that their systems have an appropriate force output range that allows users to achieve the signal-to-noise ratio that allows them to perform their desired task adequately. Broadly speaking, our study has shown that users can leverage haptic sensory pathways to interpret task-relevant information even when confronted with noise. Thus, haptics can be an important modality to consider in the design of intracortical brain computer interface-based devices to achieve naturalistic control. Thank you.